Record again. Hey, I'm going to share the screen, share the PowerPoint. And here we go. So I'm going to start now. Thank you, Aditya. Okay, all. Welcome. It's Friday again. I have the feeling that it was Friday just yesterday, and I was talking to you just a couple of hours ago. Like things go super fast, especially when you are old like me. So last week we were talking about volcanoes. We talked about mountain as well, and it goes as a follow-up on the previous lectures that you had from Aditya, for instance. So we're leaving the mountain and now going down towards the coast, and we are in the floodplain. And what we find in the floodplain mostly are, like you can see on this picture on the left side, rivers, water going up and down, so floods sometimes. And it's also a recreational area, so a lot of people there, but also a lot of people in floodplains because it's the easiest place to live and to develop. When you look at the photograph on the left here, you can clearly see that developing agriculture is quite easy on those locations. Developing cities will be easy in this location. And in Japan or in Indonesia, it's about the same. Most people are concentrated in the floodplain. So because we put a lot of our economic assets in the floodplain, because a lot of us human beings live in the floodplain, well, it's then a very important space, and it's an important space to understand. And one way to understand it, either if we are interested in resources or in hazard, is to understand the geomorphology. So once again, why geomorphology is so important? Well, when you think about geosciences as a whole, first, let's think about the long-term changes, long-term event, geology. So we look at rocks, million years of change and different elements happening through those different million years. This is very important, but if you think about everyday resources in agriculture or fisheries or developing a city on some ground, a shorter time span of the knowledge is also very important. And for that, we are going to use geomorphology, because geomorphology, through the recording of landforms and past processes, like last week, last month, the last 10,000 years, the last 100,000 years, is going to give us an indication of how the landscape is evolving over a long time. Okay? So when we have those information, then we can make better choices. Let's say, for instance, you are interested in buying a house just next to the Progo River. If you look at the Progo River and dengar ya.
You can mute the Abdul Razak, please. Maybe they don't realize that audio is on. Yeah.
How do I mute everyone?
Okay, already.
Okay, thank you. Okay, so I was saying, when you, let's say you are in the age of Mas or Pa Aditya Saputra, and you want to buy a new house because you have a bigger family and you have more children now, so you need a bigger house. And you're going to think, where can I buy a house? And if you look at the weather record or the river record for the last 50 years or 80 years, you're going to have some ideas of the flood, the dangerous areas, and also maybe some idea of, I don't know, the last volcanic eruption, the last few volcanic eruptions at Merapi volcano. So you think about all of this and buy a safe house for your family. And you pray, inshallah, that God is going to help you in that choice. But geomorphology can be also a very good ally on this, because geomorphology is going to show you not the last 50 years, not the last 80 years, but the last 2, 3, 4,000 years record. And you will be able to know whether you had a flood in one place or you had an earthquake somewhere. So when you want to buy your house, you can make better choices. Okay? So that's very important. Okay, so today, what are the objectives of the lecture? So I would like to understand how rainfall transforms into runoff. So when it gets to the catchments, how do you see this? How the water catchment characteristics influence the runoff. Know the role of urbanization on runoff. Know the different type of river network and understand the logic behind the construction of various river landform and planforms. So that's plenty. That's a lot of work. So because it's just a huge amount of work, I'm not going to do everything today. And it's most likely that we'll do river floodplain this week and next week as well. Okay, so those were the two John objectives. And let's see if I can mute the person talking. Yes, okay. So from rainfall to runoff. So how do we go from having a rainfall on a basin down to the runoff in a river? When I say basin, it can be catchment as well. So let's look first at the world map here of the water balance. So we have the precipitation minus the potential evaporation in centimeter per year. So when we have minus red data, the water balance is negative. It means that we have more potential evapotranspiration than we have precipitation. So overall, even if it rains, most of the water will be evaporated from the catchment. And when we are in blue, then it means that we have more rainfall than potential evapotranspiration, so that precipitation has the chance to stay on the land and flow into the river, or as a river. Okay? So I was trying to get something better. Hold on a second. Okay. So when you look at this map, you can very clearly see that all those countries here around Japan, Indonesia, Malaysia, Papua, all of these are in the positive side of things. Okay, so that's why we have, when we have hujan, we have, when we have rainfall, we have a lot of discharge. So for the story, since we have students from Japan and students from Indonesia, in Indonesian, you call it the rainfall, hujan, right? And in Japan, they call it ame. So ame is the rainfall. And those countries here have positive balances. And we have different other places where we have balances that are negative, like in most of the US here. We can talk about it in a second. In South America, in those region of South America, we're going to try to explain those. And then we have this long belt here, which is made mostly actually of negative balance. So when you cut through, sorry, I was going to find a word, I can't find it. When you think from north to south and you make almost an outcrop of this data set, you can see that we have generally this kind of curve for the precipitation minus potential evaporation. So it's almost like neutral, then it goes up, then we have a positive balance, then a negative balance, and then a positive balance, and then the exact same thing in the southern hemisphere. So why is that so? So try to think about it for 1 second. Why do you think that we have geographically those distribution? And I give you 2 or 3 seconds to think about it before I give you the answer. And it's the time for me to get a coffee. When I go to Indonesia, one thing I love is the kopi luwak. Kopi luwak is really, really good. Even if it's a bit disgusting, it's really, really nice. And it's very expensive outside the country. I think it's maybe one of the best coffee in the world.
Only rich people can buy that coffee.
Yeah. But I'm not rich, so I have to go to Indonesia and buy a small bit, a small portion.
Yes.
Okay, so let's go back to our potential evaporation and precipitation. So what do we see here? Okay. Well, you can see that we have first a gradient which is linked to temperatures. So when you are in the intertropical belt in this region here, because you have a lot more of sun energy, then the evaporation potential is higher. And to compensate it, you need much more precipitation. So only the weathers that are very wet, like here in this region of the world, for instance, compensated very well. And this is the presence of the sea around it. You have very warm seas in these areas. You have also very warm seas in those areas. So the old Java Sea is not very deep. It's very shallow, less than 100 meters. So all this area actually is very good in creating a lot of moisture. So one, that blocks the sun energy, and two, at the same time, it also allows a lot of rainfall that are compensating the evaporation. You have something similar in this region here. And when we are at the equator, which is this line here, this line here, the equator, because the atmosphere is thicker, so you have more atmosphere than at the pole. So when you are near the pole, I don't know if you know about this, the atmosphere is much smaller. And because the Earth is spinning, like when you spin something out in your glass, you can see that it's expanding on the side. And on the Earth, the atmosphere does exactly the very same thing. And because it's hotter as well, then it tends to expand further. So you have this phenomenon here where in this area, you have actually more rainfall. And then when you look at it, you're going to tell me, well, Chris, your story is very interesting, but why is it that in this region here, it's so dry? Well, if we start with this, you can see that you have a fringe which is very long going down this way. What do you think is there? What do we have over there? And the answer is quite simple. We have this huge chain of mountains, which are the Andes. So when the air masses that travel this way from left to right, or from here, from west to east, they go and bump around the mountain here. You have actually a lot of rainfall eventually just by the coast. And then all those inland areas here are very dry. And that's where you have the Atacama Desert. So in this region here, because the rainfall are not coming, it's very, very, very dry. It's very different from what you have in this region here, where you have the Amazon forest, and the Amazon forest have the different effect. Another desert that you have for other reasons that are continental reason, here you have the Sahara and other smaller deserts that are very hot. If you continue further towards China, you have the same, for the same reason that you have a desert here, you have also a desert and continental desert in the mountain in this area, because it also doesn't rain much. Now, if you look at USA is also very interesting, because especially in California here, naturally, we don't have enough water, basically. So people have been draining water, moving water around. When you think about the Colorado River, pumping a lot of that water to do agriculture. But unfortunately, the Colorado River almost doesn't flow to the sea anymore. It's almost a trickle. And one of the reasons is because the natural conditions are not that great in this part of the US here. And then Australia, of course, is also very, very dry. Okay. So you can look at those maps in more details, but those are the main landmass, and I just don't want to go further on those. And there is a small explanation actually of what I just said in a more polite and polished way just underneath here. Any question on that? All happy? And if it's the case, we can go next. Okay, so how do we get runoff? I was telling you that this balance just before between precipitation and evapotranspiration is important. And that gets us to the runoff elements. So I'm going to move that again. I'm using Zoom. So on Zoom, I can see my face, which is not that great, but it's also a bit of a pain sometimes because it just stopped me from seeing the PowerPoint. So how do we get to the runoff? So we talked about evapotranspiration, that we can divide between evaporation and transpiration. What's the difference? Transpiration is for greeneries, vegetation, sorry, it wasn't coming out, for vegetation, when evaporation can be on any surface. And from the evaporation, that can be from the soil, from the open water, or here, or I wrote it actually, or from the plants, okay? And one way that you can look at it, you can see here on this small lake here, you can see the shoreline that can go up to the top white level. And all of this, actually the water went down. This is usually by evaporation. So you have rainfall, the water goes up, and then you have evaporation, and then the water goes down. And that level is going to be linked to other levels. And what's going to happen is that some of the water will go down to the ground. This is what we call the groundwater. And the groundwater will be usually located at the interface between the soil, which is here permeable, and a more impermeable layer. That can be the bedrock. That's why we have drawn here those lines, like the water going through the cracks. But you can have other and more layers in between. It's the case in Indonesia a lot when you have, for instance, a large eruption. It's going to create very fine ash material that are going to cover the land. And then soil will build over it, and it's going to be buried after a while. And those very fine ash soil, once they are weathered especially, tends to be very impermeable, so that the water will flow on those. And those connect down to the river, and that's when you get your river level here. So this is this process, which is here. It's called the Horton overland flow. That's the part here. Then we have the subsurface storm flow and the return flow, which is here, actually the groundwater flow and the return flow, which is underneath. Okay. So that's how you can think about the water going through the landscape. And you can tell me, oh, and what about the geomorphology? How is it relevant? Well, wait, we are getting there in a minute, but those processes are very important to understand then the landform and the landform creation and the role of water in creating those landforms. And when you look at them in more details, well, those are the different elements working together. That's how you relate your soil and your geomorphology to the infiltration and to that schema here. Okay, so I will let you have a look at all of those details on your own time. I think it's not necessary that I go through all of that, especially because you might see some words that you don't recognize. So I invite you to take a dictionary, or paper dictionary, or Google Translator. Google Translator is your best friend. I'm sure it's my best friend too. And you can use and try to learn actually those different elements and how they work together. Okay, so now let's go to the runoff generation. How do we get to this part? So in this schema here, I show you the pathways of water. You have different pathways as the groundwater through what we call the vadose zone here, and on land and through the bedrock. how do we create this Hortonian flow first and then the surface flow? Because this is what is going to also interest us as a geomorphologist, as how the water interact with sediment, with landforms to create new landforms. Well, we have to remember that to create the runoff, which is the water running on the surface, you have a lot of different processes occurring simultaneously. Unfortunately, it's not a simple thing, but we're going to try to divide them into different points so that we can understand one element at a time. But remember, none of those work alone. Everything works together. So you have to remember that when you think about those different processes. Think about the fact that what we'll see also can shift in time. Nothing is set. Everything is moving quite a lot. And then even if we look at one process, a lot of what we call the antecedent elements are important, like the antecedent wetness condition. So when you have a rainfall, let's say, that goes on land and it hasn't been raining for 10 days, then the water can percolate through very easily. But if you have the same rainfall that comes on the very wet land, then you're going to have a very different answer. So when you think about one process, you have to think about how does it happen, but also when and where. What happened before that very same process? And to calculate the Hortonian flow, I will keep all the maths at bay for this time. We can do mathematics maybe another year or later on. When we think about the wetting front, we think about the lengths here of that slope, which is XS, to calculate actually QHO, which is the discharge at the exit of that slope and the water that gets in. So you will see very often those different elements and the name of the wetting front so that you know those. And if we do a graph, so we stay away from the numbers and we just put it on a nice graph, and there is nothing that a good, nice graph, we need at least 3 elements together to understand what is happening and what creates the runoff. Of course, we need the precipitation rate, we need the runoff, and we need the infiltration curve. So the infiltration curve is also very important, if not essential, for soil to try to understand how the water gets in the soil. So let's say over time, you have rainfall. So we have, this is the precipitation rate, which is named here high. When it starts raining, so it's raining here, you can see that green curve, it's raining. We have a runoff, which is almost nothing at first. And that runoff is going to slowly increase. And it slowly increases and it slowly changes because the infiltration rates change. So at the very start here, all the water which is being precipitated, all the rain is being infiltrating in the ground. And once all the water cannot be infiltrated in the ground, but less and less is absorbed because there is already water inside, so it's more difficult to get more in, then you're going to see the runoff increasing. So instead of having something which is the same amount of water coming out of your basin, you're going to have an increase. And this increase is actually just compensating for the infiltration change. And then when the infiltration cannot occur so much anymore, it's like really saturated. So it's slowly taking water in. All the water which is being precipitated is going to have an effect, a direct effect on the runoff. And that's why here, when we have this curve, which is going up and down, boom, 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 we have the same effect here on the runoff. We don't see that effect on the infiltration because the infiltration rate is much lower at that time than the precipitation rate. So even if we have change here, the infiltration is still the same, slowly sinking, sucking water, but very, very little. And everything else goes out on the land and is flowing on your basin or your catchment, okay? So that's what is also written here. You have the infiltration trends, which is the infiltration rate that decreases over time as dry pore spaces between soil particles fill with water. Rates of infiltration drop and become steady as the soil saturates. After saturation, the infiltration rate is a function of soil hydraulic conductivity. So that horrible word here, soil hydraulic conductivity, is the fact that once the old soil is full of water, then it's going to move the water slowly. And that's the soil hydraulic conductivity. And there are some equations for that if you want to make some calculation, but let's get through the concept first here. And then when you think about the runoff trends, it does the opposite. So because the soil cannot absorb, suck the water anymore, so you have the opposite, and the water which is being precipitated goes up. Okay, before we go further, this is very important for slope geomorphology, for floodplain geomorphology, because when you have a rain event, if you have a soil or rocks that are very porous with big holes in between, the water goes through and flow underground and nothing. But if you have soils that are much smaller, like with smaller particles, like you have in Indonesia, you have a lot of clay due to the alteration of the material. You have a lot of clay because of marine material, and you have a lot of clay and sand because of the volcanic eruption. So in that case, the water gets absorbed, but the hydraulic conductivity is much slower, meaning that you have a lot of water running on top because it cannot get into the soil, it runs on top of the topography. And then you have debris flow, you have bungir, you have a lot of different forms of storm events that raise very quickly the water level. And in turn, because the water level rises quickly, then you can carry a lot of material. Then you can have erosion. Erosion is very important to understand the landform in geomorphology. And this eroded material will be transported and deposited somewhere else. So you have landforms creation that can be very fast. So if we go back to our map earlier, let me go back if I can. Here we are. So if we go back to this map, what does it show actually? Well, if we think about the region where we have a lot of rainfall and it's not too cold, the cold region are a bit different. For the warm region with a lot of rainfall and a balance which is positive, all those areas here mean that we have a lot of rainfall and that the lot of rainfall goes into the ground and that ground absorbs it quite slowly actually, because we are in a region when it's hot, where the material is altered very easily. So we have a lot of very fine material so that the water doesn't get so quickly into the ground, so it flows on land. So for those islands like Japan, like Indonesia, like Papua, and even New Zealand in some ways, and the Philippines, they are very narrow lands with very steep slopes, even in the lower floodplain. So we have high energy flows and we have a lot of debris flow. We have a lot of floods happening very quickly and a lot of rivers there. In places like in the Amazon basin here, where the slope is much gentler and very long, we have then very large rivers going slowly to the sea and creating a different geomorphology. So you can see those distribution here are very important in understanding the type of soil that we're going to have, the type of formation, soil formation we're going to have. And it's also very important to understand how the water will behave on land, how it interacts with the soil, and what kind of landform you're going to have. I'm trying to go next, and next, going back to what I was talking about. Okay, so you see that curve here. When you look at it, it's like, nah, that's not geomorphology, that's hydrology. But to understand geomorphology, you need that curve. It goes also the other way around, and that's when it's powerful. That's where geomorphology is powerful, because we know there was a relation between the runoff, between the rainfall and the runoff, and how it creates different landforms. Then you can go back to then those landforms, even if you don't see the water, and look at, oh, that's a river terrace with a very large block inside. So we had high energy flow. So that's a fan which is very steep. So we had maybe a debris flow inside, or a banjir, or any type of flow that was very quick. Or you can look at it and we have like a very flat fan expanding. And in that case, well, you know that you had a very slow flow, something rather different. So I'm going back to Professor Saputra and his house buying experience. And being in Indonesia, or if you are in Japan as well, virtually there is no 100% safe place. Everywhere you have a lot of processes, you can have hazards and phenomena from the natural environment that can bring a hazard. But knowing geomorphology as a citizen, you can make good choices about where you want to live, where you want to build. And that can be, of course, the runoff, but that can be also looking at the fault lines, for instance. Okay. Next, Horton overland flow. If rainfall exceeds soil infiltration capacity, that's what we saw. Water fills the surface depression, then water spills over downslope and down to the stream. So in that graph here, I was talking about straight away water going down the slope, but topography can be a bit more complex. And in that case, we also get first the surface which are in depression that get filled, and then that spills and go downstream. And most of the time, it's going to look like this. You're going to see overland, and that's in California here. You can see that the water just flows over the land where you don't have a channel in this kind of shapes here. If the water was flowing all the time in this location, then you will get slowly a channel. It's not the case here. Okay. Here, I'm telling you that actually the direct precipitation, so water being precipitated on land, is not the main driver, it's something else. And when you look at that, you understand why. Because the main driver is actually to be the groundwater connected to the different channels. And if you zoom now, that's the next concept, how the groundwater interface with the surface water. You can see very clearly that you have something which is very much linked to the water table here. Okay, so let's take 1 second. I'll let you look at the graph and try to understand the different words. During the 2 or 3 minutes I'm giving you, have a look at Google Translator and look at what is the Vado zone, what is the phreatic zone, how do you call that in Indonesian or in Japanese, depending on where you are in the world. Okay, so this graph actually continues the discussion I was having with you on water being incorporated in the soil. So when you have water that comes from the rainfall on top, it's going to go into the pore and that contains some space and air, then goes down. And there is a zone here which is not fully saturated, but with a lot of water already, which is going to be called the capillary fringe. And then you have the groundwater there. The reason why you have those zones here, it's because when the water falls from the sky, that's rainfall, get on the ground, it's going to go in between the water, the different small particles in that zone, and then going towards the groundwater. But very often you're going to have a lot of small droplets of water. And when you get closer to that location, it's like when you are in the traffic jam in Surakarta or in Kobe or wherever you are, when that car here is stopped in the groundwater, nobody's going to go straight at the same speed and stop straight away. There is a small zone here where people go a bit slower and start braking. So for the water, it's the same. We have a braking zone. Actually, we have different zone here, but it's more like a gradient going slowly into the groundwater. Okay? And that's what we explain here. We have the capillary reaction here that pulls the water into the pore space. And at the same time, this is actually going slower and slower, while the water on top infiltrates by gravity. And those different zones then have different names. So we have the saturated zone here, which is the phreatic zone, and the top part, which is the that's location here, which is the unsaturated zone or the vadose zone. Okay. And connected to that groundwater, then that's when you have your river here. That's when you can see the water popping up. Now, if you look at your river, that very river, the level doesn't stay all the time at this level. It's going to be all up and down and up and down. And this is due to the rainfall. This is due to change in the water table. You can have a lot of different things. If you are, let's say, in Palangtritis, and you look at the Progo River going out near Palangtritis, the Progo River is going to go up and down every 6 hours because of the tide. So because the river is connected to the tide, the sea goes up, so that the river here, this level goes up. And then the sea level goes down, and then it goes down. So you have this movement all the time along the end of the Progo River. So you have a lot of different phenomena that are connected to another. And then, of course, when it goes up and down, if you have a high tide, for instance, it's going to modify the speed of the river. So let's say you are at the high tide. So the river, which is here, meets the water level of the sea, so that this angle here, the slope, is much smaller. And because it's much smaller, you have less energy. And less energy means that you transport less material. So you're going to have deposition at the bottom of the river. And then the tide goes down. So the sea level goes down. Then the water level of the river go and meets it. And when it meets it, you have like a larger slope. Larger slope means more energy, and then you have erosion or transport again of the material that was deposited. So you see, rivers are very complex system because they interact with the atmosphere, they interact with the groundwater, they interact with what we call the base level. And here I said the sea level, but it can be a lake, it can be another river. And that's the name for that is base level. And when the base level change, so is the profile of the surface water. And to understand, to assess, to measure those changes, scientists are using what we call here a hydrograph. And the hydrograph is that curve here, the blue curve that we have here. So that's going to be here the river discharge in cubic meters per second. You can have other way of measuring it, but that's traditional. And after rainfall, for instance, when you're going to have an event where you have a peak in your river discharge, the water level will go up. We're going to divide the hydrograph in two parts. We're going to have the rising limb with the soil which is filled of water at that time. So the soil is full of water and then the water level goes up. And then we have the falling limb. So we have less water available. So the effect of the rainfall is gone. And at the same time, because there is no more rainfall on the ground, then the soil actually is losing slowly also of its water. And that's the falling limb here. And we have also what is called the base flow. So the base flow is what you have before this exceptional event of rainfall here, and after its consequences are not seen anymore. And this is called the base flow fed by the groundwater. So that's this curve here, okay? And this is the reaction to the rainfall here. So you can see that the rainfall during a rainfall event, the intensity at which precipitation falls on the landscape is often variable. The peak rainfall, a measure of the greatest intensity of rainfall, does not necessarily occur in the middle of the rainfall event. Therefore, the peak and the center of mass, which is here, the center of mass of the rainfall event, are usually actually not in line, okay? And then for the discharge, as the precipitation falls across the landscape, some infiltrates, that goes through the soil, and some runs off, so straight into the river. And it goes into the river channel, causing discharge and river stage. River stage is the height of the level height of the river to rise. As the soil fills with water, more precipitation enters straight the river channel as the runoff, and groundwater flow and surface storm flow. So all of those here contributes to the runoff. The stage rises until reaching the peak, which is right there, or maximum discharge resulting from the rainfall event. And then as water drains from soils and from the landscape, then the river stage begins to fall, eventually returning to the base flow, which reflects normal groundwater discharge to rivers in humid region, okay? So here it's written humid region, like in Indonesia or like in Japan, because in places, let's say like Namibia in Africa, where you have a balance which is negative, you don't have actually enough water to feed into the river, and then it all drains out. Now, the shape of the hydrograph and the way it's working is going to change depending on the shape, the size, and the type of drainage that you have. So that's the next topic here. It's 45, we can continue. So the drainage basin and the rainfall. So at time T1, so it's raining everywhere. So we are here. You can see that your river drainage in the blue line, you have a bit of water coming through, but it's not concentrated yet. Then at time T2, when you're here, you have more and more of that water that has been filling the pores, so you have more and more river contributing. And then when you are at the peak, you have actually all the system which has been interacting. And then that's when you get actually you're getting towards your curve. But you see when you have water falling in this region or this region here, even at T3, it takes time for the water to go down, so that your discharge calculated here is having a lag. So when you have your peak flow here, peak rainfall, the discharge flow, there is a time lag in between the two, and that time lag is due to the shape and due to the time it takes for the water to get to the exit. So when you look at it from a graph perspective mixing the two, if you consider this area here, the water that has been falling in from this is going to create a small peak discharge. And then when you have more water contributing, then you get more elements contributing to discharge until everything is actually contributing, and then you get a larger peak. Okay, so that's the concentration and it's bulking up. This graph here, the hydrograph, is going to be very different depending also on the shape. So we just saw that depending on the size, 1 square kilometers, 10 and 100, you're going to have actually a different amount of water. So if you were to use that curve and draw the integral in between, underneath, that integral is going to be a function of the size of the basin, but the shape of the curve is going to be a function of the shape of the catchment. So when you have an elongated catchment like this, you're going to have actually a rather quick concentration. When you have a basin which is about this shape like this, you're going to have something which is a bit smaller. And then when you have a larger basin, your hydrograph is going to create something which is a bit more like this. So when you have a narrow basin, you usually have a faster concentration. And the reason for that is that the time it takes for the water to go from this location down to the main channel is going to be much faster than when it's much broader like this. Okay, so I'm going to finish with this last concept here with the hydrograph, chemograph, and sedigraph. So you're going to leave that lecture with almost no geomorphology, but you're going to see from the next lecture, understanding that is going to help you understand the geomorphology. And geomorphology is not only the landform, it's also the processes that make those landforms. And here we're looking at the processes. So in terms of hydrograph, you have your rising limb that does that. When you look at the chemograph, which is the chemical elements transported into your graph, you're going to have a graph that does something like this. It goes up over time, and then it's going to go down. T1, T2, T3. Why is that so? Well, this is the concentration. So if your chemicals are on land, when your hydrograph peak is rising, it's carrying more and more of this material. But after a while, it's not going to take more elements. There will be more water flowing, going from the sky, from the rainfall. So all of that is not going to add more of the solid concentration. In that case, it's going to go down. And what has been transported, what was available from the ground at first, is not available anymore. It has been washed. So you're going to have actually less material towards the end. So when you have the peak that goes down, you have less material, but it's also because you have less energy. So it's going down, less water, and then the peak recedes again. Okay, and that's when you are at T3, you go back to the base level. When you think about sediments, we have something which is quite similar. The sediment concentration is going to increase with the energy. So you have a rising energy in the peak, so more energy, so more sediment transported. And then when the peak recedes, you're going to actually have less sediment and less energy until it goes down back to what was at the start. And if you have seen floods, you're going to see that the water is going to become more turbid with a lot more sediments and material transported. And then when the flood recedes, then the water is a bit clearer, okay? And that's what we see in those graphs. Actually, it's 50, I can talk about the following. Now, in geography, in geomorphology, those graph here, this schema here are for a simple ground cover. But as we know, we can have natural environment, semi-natural environment, or fully urban environment. Think about Jakarta here, and think about, I don't know, Boyolali here, for instance. So very different type of environment. And this is going to create actually a different type of response of your basin to the water which is being precipitated. So let's look at this image here. So when you are in natural ground cover, we have about 40% which goes up back into the atmosphere in evapotranspiration, about 10% that goes into the runoff, and 25% in shallow infiltration, and 25% go and recharge the groundwater with deep infiltration. When you start to have 10 to 20% of impervious surfaces, those are surfaces where the water cannot get into the soil, like the roof of the house, like the concrete on the ground. You change the balance to 38% evapotranspiration, 20% runoff, and this is the 2020 infiltration in shallow and deep infiltration. So a change here. If you increase again the impervious surfaces to 30 to 50%, so a suburban environment, in that case, you're still going to have about 35% evapotranspiration, but the runoff is going to increase to 30% because the water doesn't get into the ground so easily. And then you get 20% shallow infiltration, 15% deep infiltration. So you see, it's important because the more urban we are, the more concrete we put into our landscape, the more runoff we are going to get. And it's going to be very important in the river discharge and in the hydrograph as well. We can see that in the hydrograph. And then if we go to 75%, 100% impervious surface, so that's the urban, typical urban environment, we still get about 30% evapotranspiration from the building. Now look, we have 55% runoff. Half of the rainfall go and flow straight on the ground. And this is not good because when you look at our hydrograph, look at the hydrograph in natural condition against the hydrograph in urbanized condition. In that case here, we are going to have actually faster, stronger, bigger, more amplitude runoff, meaning that more amplitude storm water, more amplitude floods on the ground. What does it mean? It also means that we have more energy. So more energy means in the river, more erosion, more sediment transported, and more catastrophic events if you think about hazard. So the construct of your basin, the number of building, how it's built, how much greenery you have, is going to be very important in changing the processes and in modifying erosion. If you put these results in a longer perspective, you can think that actually the geomorphology, the landforms, are going to change over time because human beings are changing, modifying the relation between rainfall and the runoff. So you don't need climate change. You don't need actually those natural explanation to actually see that human beings have an impact on erosion, on the runoff, and on floods as well. So I'm going to stop with this today. We're going to stay here. We are going to continue from that point next week. So go back to the PowerPoint. If there are things that you have not understood yet, make sure that you go back to it and you study the PowerPoint for next week. So that's all for me today. So I wish you a good Saturday and Sunday, good weekend to everyone. For those of us in Indonesia, a good Jumatan today as well. Take care of yourself, your loved ones, and your family on that very important day. And do not forget to study for next week, and I will see you next week. If you have any question, you can ask them. We still have 3 minutes. I'm happy to take any question.